So as I said before, how likely a person is to respond in a particular way to a particular item depends on how much of the trait they have on that underlying continuum and the characteristics of the item. And in a one-parameter model, that characteristic is the difficulty of the item laid out on the continuum for that trait.
So Alan, can I just break in here because this is something I've never really grasped. What did happen to the idea of error, meaning a person is responding incorrectly or the measurement is imprecise? It's just not in this anymore.
No, it is. I mean, in all of our tests that we develop, we have statistical ways of characterizing error, and they're actually very similar to classical test approaches. Like reliability, we can calculate the reliability of all of our tests. The beauty of it, though, is it's not just a summary measure of reliability. We can estimate the amount of error at each point along the continuum. And we can plot the error curve, which we always end up showing at the extremes of the distribution you have more error. So, but it's very similar in principle to classical statistics. Precision is another statistic that we always will estimate, and we'll look at the amount. Basically, it's a standard error of the measure across the full continuum, not just a summary, but across the full range. We can look at accuracy, and what we usually do when we develop CAT measures, we'll look at how well they represent the entire item pool. Those are all kind of measures that reflect error. So it's done, but it's done in a somewhat different way. And it gives you the same kind of information that we want with classical test theory. How well is the measure working? How much error is there? Is the error random? Is it systematic? And then we get into more sophisticated issues of what's the breadth of the measure? How well does it reflect change when it's occurring? Is the change clinically significant? So those are all in there. But thanks for the question. So, you know, when you try to compare and contrast, I've just kind of summarized this slide. And so there are some advantages that people see in the item response theory approach. The other advantage that I don't think I put down here that I've learned over the years is it's very easy to improve these kinds of measures as well. Whereas with classical test theory, it's much harder. You tend to use a measure that's been developed and you keep using that same measure over and over again. And it's much, much harder to improve them. Whereas IRT-based instruments, once you begin to characterize the quality of the measurement, you can identify whether there's some problems and gaps, and you can go back into the field, write new items, develop new measures, add them to your existing pool of items, recalibrate the items, and add the new ones into your scale and improve the scale. So we did that with the first test that we developed 10 years ago, and I think we were the first ones in the health field who then went in and improved. We added new items, we identified certain areas, we had some ceiling effects that we weren't happy with, and we went through and we recalibrated new items. Clinicians helped us write better items, came out with a new version of the tool, and boom, off we were running with a better tool. So that's one of the big advantages from my point of view. Now, we spend a lot of time in our group building item banks. So I want to talk a little bit about this because those of you who might be interested in this approach to measurement need to know what you're getting into. This is not a, and I tend to be flipped, so my apologies. But I've had people, like I was working with CMS, and they want to use an IRT-based measure of function, but they want to develop one in 30 days. You know, it's this kind of thing. And it takes several years to do this kind of item bank development and testing. So you need to be aware of that when you're getting into it. So I'll talk about some of the principles on how you do it. One has to consider, the key is you're trying to develop a pool of items that are going to best characterize the full continuum of whatever trait it is you're trying to measure, okay? Now, to do that, you have to evaluate the information that each item that you're considering is going to give you about that underlying trait. It's referred to as information function. And you can plot that information in various ways that I'm not going to go into. But we have methods, they're well characterized, and it allows us to look at to what extent does an item bring something unique to the party, basically. Because in many classical tests, what happens is we get tons of items in the center of the continuum of whatever trait it is we're trying to measure. And there have been many, many articles in the 80s and the 90s that have analyzed classical tests and shown that the items tend to overlap and they group in the center. So when we build tests using IRT methods from scratch, what we're trying to do is get items that will give information across the full continuum. It's called information function. And if you do it well, when you characterize the full test, the test information will be the mathematical sum of the individual item functions, and it'll show how well you cover the full continuum. So conceptually, it looks like this. Each one of these curves is an information function of a particular item. And this is what you're striving for. You're striving for items that will cover the full continuum. Here, this is a functional outcome continuum from a very low amount of the trait to a very high amount of the trait. That's what you're aiming for. And then the test information function would look something like this if you do it well. That's the ideal. Now, none of them meet that ideal. But you might as well know what we're striving for. What tends to happen is exactly what you would anticipate, those of you who have worked on measurement over the years. The extremes of the continuum are the part that are most difficult to characterize. Most difficult to characterize. Now, this is terribly clinically and research relevant because if you have a very truncated scale, even if it's a nice IRT scale, it's not going to be very reflective of change. And in almost all cases, ultimately, we're interested in characterizing change. And so, to me, that's one of the big challenges, whatever technique we're using, is to be able to really characterize the ends of that continuum. The middle, I can show you example after example where we got the middle covered beautifully, and the ends much more difficult. So, instrument items are built that will cover the entire continuum of whatever the ability trait is, and items will provide different information if you've done it well. The scores are then calibrated to an equal interval scale. It's the Logit scale, and this provides the foundation for adaptive testing. Now, before computer adaptive testing came along, we had IRT methods. Rehab was one of the first fields to adapt and use IRT methods. And I remember when we first started doing that. In fact, I think one of the first articles in Health on IRT was my colleague Steve Haley, who works with us at BU, who characterized the SF-36, working with John Ware back in the days of the Tufts group. And they published one of the first articles characterizing basically the flaws of the SF-36 instrument using IRT techniques. But it wasn't very exciting because you couldn't do much with it. You know, you could improve measurement a little bit, but it didn't excite the field terribly. It kind of showed the flaws of some of our traditional instruments. We were able to improve it somewhat, but we still had lots of problems. And one of the biggest problems was if you were really trying to characterize the full continuum, you ended up with huge instruments, very long instruments. I remember the first scale that Steve developed for pediatrics, no one ever used because it was humongous. It had hundreds of items in it. But it was exquisitely built, and it characterized pediatric function extremely well, and no one used it. You know, that was the problem with IRT. Then along comes computer adaptive testing, and that, in my way of thinking, is the real breakthrough. The combination of computer adaptive with IRT allows us to really improve in a significant way some of the challenges in measurement that we've been trying to achieve. Because for years we've wanted it both ways. We want comprehensive, precise, sensitive measures that can be used in minutes, right? I mean, that's what we all want. I mean, I can't tell you how many times I have been asked that question. I mean, it's got to be comprehensive, it's got to be precise, it's got to pick up change, so it has to be sensitive, and it only has to take me a couple minutes to use it. Why can't you do that, right? And so computer adaptive techniques, I think, give us the possibility to do that in a way that we've not had before. Lots of limitations, but I think it's a significant advance because it allows us to develop more practical instruments without sacrificing the psychometric properties. We've had practical instruments, short-form instruments. The problem is they've been psychometrically dissatisfying because we give up so much in order to get the practicality. So this, for example, ceiling effects are a huge problem with many of the instruments we use in rehab today. I pick on the FIM frequently when I talk about ceiling effects. In all fairness to Carl Granger and his colleagues, it works quite well in inpatient rehab. But people have used it much more broadly and widely, and it doesn't work well in those contexts, mostly because of the ceiling effects. The other problem are instruments that have been developed, they're not precise enough. The gradations in between different components on the continuum are too crude, and so people are unhappy with that. That's been a common criticism of the SF-36 that many people use in the health field. People feel it's just too crude. To say nothing about the SF-12, the SF-8, and the SF-1. But that's what's driven people in that direction, is because we want something that's really practical. You can develop long, exquisite tools using classical or IRT techniques, and the problem is no one will use them. Okay, so that's the problem. The answer we've known for years is you have to just figure out a way to make it more practical. It would be practical if you could develop really exquisite, comprehensive, precise instruments, but then only use the relevant components of that instrument for a particular patient, and not have to use all what might be an irrelevant component of that instrument. So if the patient, for example, is functioning at the very low end of whatever outcome continuum you're interested in, asking them all kinds of questions at the high end of the continuum is the waste of their time and your time, tells you nothing important. But in classical methods, you have to use all the items in the tool. You can't be selective. So that's what computer adaptive testing allows you to do. And that's why it's built on top of these IRT batteries. You develop the tool using IRT techniques. You administer it using computer adaptive techniques. So it's tailored. It's individualized. And it, using computer algorithms, it selects items from the calibrated pool that you've developed based on the previous responses to earlier items. So it's done in real time. It's done based on the algorithms that you've developed ahead of time, and it's based on decision support rules that you, the investigator, determine. And I'll talk a little bit about those. And that's what makes it incredibly efficient. So we have instruments that are hundreds of items long, and each scale takes, on average, 8 to 10 items to generate a precise score of where that person is on that particular underlying domain. That's a considerable savings. You go from 100 items to 8 to 10. So I think that's one of the exciting elements.